SwayamPrabha. Digital India. Educated India.
In this lecture, we'll be discussing the standard method of linearization around a reference point through that Taylor series expansion. And then we'll apply this concept for the pendulum system and how we can get two different model of linear state equations of the pendulum system. And then the linear state equation, what we will be finding from this lecture, we can validate to the previous lecture, what are the findings we had. Then we'll conclude the lecture. Now we'll be using the concept of linearization. How can you use this concept to convert the nonlinear system into linear form? This is called linearization technique. So let's consider a scalar function. First, we'll assume a scalar function, then we'll extend to the vector function. A scalar function f z, which is differentiable. So the function behaves something like this. This is my fz function. This is z is the independent variable. And let's assume the function something like this. Now, it is found to be equilibrium point or some reference point somewhere here. For example, this is my some reference point, or you can say the equilibrium point. And around this point, we'll approximate this nonlinear function, something like this, which is basically first order approximation. We can say at z equal to z bar. Now, for values of z close to z bar, we can replace fz with its approximation using the Taylor series. Using the Taylor series around z bar, we can write f c, which is equivalent, we can write f z bar plus df dz, which can be approximated at z bar, and this is z bar. So this is very standard expression if you apply the Taylor series expansion to a function fz. Here we are not considering the higher order terms, because the magnitude of those higher order terms are quite less compared to the first order terms. So we are neglecting those terms. So this is very basically first order approximation around z. We can say this is first order approximation around z bar. So here basically the main concept of this technique is how the system going to evolve around this equilibrium point or some reference point z bar. Now, this is basically scalar case. If you extend this concept to a higher order functions, so if you consider a vector valued function, if you consider a vector valued function, consider like this. And if you also assume, if you write the expression, z dot equal to, let me write f g u, for example. So this is more complex cases where we are having some disturbance or any external perturbations or some controls on the system. Then we can write in general form in this expression, right? Where g is basically vector valued function, or g basically vector, and u is it can be also vector. So now in that case, we can approximate this function. Let me write this equation number 1. We can approximate this equation number 1, approximate of f z u at point z bar and u bar. So this is basically equilibrium point, I can say. Some equilibrium point in g bar, u bar. Some fixed point, we can say, is in the previous case, we had only fz. Now we have fzu. So there are two different states, and there can be two different equilibrium points. So in this case, we can extend the above concept. We can approximate fxu, this system. We can write equivalent. We can write f x bar u bar plus tau f. There's a typo. It should be tau. It should be tau in this case. It should be tau actually. So now we can write this expression tau f, tau c, g bar, u bar, c minus c bar, plus we can write tau f, tau u, c bar, and u bar minus. So this is also first order approximation, but this is for different multivariables where x and u, there's two different variables, state vector. So where we can write where tau f, tau j equal to tau f1, tau c1 dot tau f1, tau gn, and similarly tau fn, tau g1, tau fn, tau gn. So this is called Jacobian matrix. This is very powerful part in this case because this matrix will be useful how we'll be finding the eigenvalues or the roots of the system and how we can comment on the stability of the system also. This is because this is a very simple method. You can come up with the conclusion on stability. I mean, we'll be talking those things later in the subsequent lectures. And here, do if, do u, we can say, we can write do f1, do u1, do f1, do um, do fn, u1, do fn, do u. The dimension of u vector is m here, so that is will go till mth partial derivative. So the dimension of this we can write n cross n, and this is the dimension of this, we can write m cross n. So this is also Jacobian matrix for the control part, but this is called state matrix, this is called control matrix, but we'll be talking later how we'll connect these things to our systems. So this is how we'll be finding the Jacobian matrix for the system. Now, if you apply this concept for a system, if you apply the above concept to the systems, can I have system f of xu and y equal to c of xu. So this is another system, I mean same system here. Instead of z we are writing x here, so it is structure wise same. And if you apply this above concept the way we have found the Jacobian matrices for a nonlinear system, then the approximations at x bar u were the approximation at x bar u bar, we can write f of xu f u bar plus dou f dou x bar plus dou f u x equal to x bar u bar u minus u bar. So this is the first order approximations of the system, and also the output equation. Okay, in the previous case we have done for the state equations. This is how we have done. Also the similar procedure we can apply for this output equation. We can apply for, so this is the state equation, and this is basically your output equation. And so here we'll apply the same concept for the output equation as well. So the output equation we can write c xu equivalent to c x bar u bar plus dou z dou x This is a very standard technique in Taylor series expansion. So if you, in Taylor series, basically we find the series of a function about some reference point. So here reference point, this is our reference point. and how we are going to find the linearized model about this reference point. So it is similar. So now it is x minus x bar plus dou z dou u x equal to x bar, u equal to u bar, u minus. So this is how we find the linearized model of the output equation. So here, if you define A equal to dou f dou x bar u bar. So this is basically matrix, right? These are basically, if you notice, this is basically matrix. And this is also matrix, this is also matrix, this is also matrix, this is also matrix. These are matrices. So we can write a matrix A, we can define, and we can define B equal to dou f dou u x bar u bar. So also can define. And this is called, in control system, this is called state matrix. And this is called control matrix. We'll coming these things extensively in the future lectures. For the time being, please remember this is called state matrix and control matrix. And also, so here, this is my state matrix, this is the control matrix. Now, this is we call state matrix for the output equation, and this is also control matrix for the output equation. So here we define C as dou z dou x bar u bar, and T we can define as dou z dou u x bar u bar. So these are basically matrix for the output equation. Now we'll find the linear equations from the above concept. From the above concept, if you write in terms of matrices, if you write from this system and this system, we can write an equation as x dot equal to, or equivalent, we can write if x bar u bar. If you look the series, this is what we'll get. A x minus x bar plus b u minus u bar. And similarly, for the output equation, we can write z x bar u bar plus c x minus x bar plus t d into u minus u bar. This is basically what we are getting from the Taylor series expansion. Now we'll come up with more compact form. Let's define sigma equal to x minus x bar and v equal to u minus u bar, and w equal to, let's define y minus z x u bar. So this is my actual values, and these are the trim values, x bar, u bar, and z. Z is the function at the equilibrium point, x bar, u bar. And from this, we can come up sigma dot equal to x minus x bar dot. Since here we are assuming x bar is constant, so we'll get x dot. And if you apply this concept for our system, this system, we can write sigma dot equal to f x bar u bar plus a sigma plus bv. And also we can write w equal to c sigma plus dp. This is quite easy, you can connect. And also it should be noted that at the equilibrium point, these values, this function yields to be 0. Or we can write the approximation is linear when f x bar u bar equal to 0. It's quite obvious because we are finding the equilibrium point, making the function we are making f equal to 0. This is how we are finding the equilibrium point. And the solution we are getting from this function, the function when f equal to 0, if the solution from this condition will satisfy this f equal to 0, for those values will come up with this condition as well. So this is quite obvious. And from this condition, we can come up sigma dot equal to a sigma plus bv, and w equal to, we can write c sigma plus dv. So this is called linearization. This is called the linearization of a nonlinear system. This is the linearization of the nonlinear system. X dot equal to f of xu and y equal to c xu. This is quite an important part of how we can come up with the linear form. This is linear form of the nonlinear system. We'll take an example of the same system, what you have considered in the previous lecture, pendulum system, and how we can come up with this form, this structure, linear model. So let's proceed. We have system example. We have system d squared theta dt squared plus g upon L sine theta equal to 0. And after the changing the variables, we had, so for the solution, we have x1 dot equal to x2 and x2 dot equal to minus g upon L sine x1. This is we have done before. And if you denote, this is my f1 x1 x2 and f2 x1 x2. I can write here x1 is obviously 0, but we can write this is my function, one function. And if we apply the concept of linearization, we can come up with the linear form. But if you notice carefully, this system is represented only with the state vector, not the control vector. So we no need to go this part. It's not required because there is no control part in the system. Just we can come up with this structure. So it means we no need to find the second part. Also in this case, second part, because there is no control in the system. So we can just come up with the first few terms in the linear model. So now let's start. So here, the equilibrium point already you have, and the output equation y equal to g of x, we can write x1 of x1 t. This is theta of t also. So this is the angle we are measuring as the pendulum rotates around the reference point. And this Jacobian matrix for this system, we can write Jacobian matrix for the system, dou f1, dou x1, dou f1, dou x2, dou f2, dou x1, dou f2, and dou x2. If you notice, for this pendulum system, we had two equilibrium point. The equilibrium point already have found for the system. Equilibrium point already you have x bar equal to 0, 0 and pi 0. So it means we are having two Jacobian matrix with the respective equilibrium point. And okay, let me write here the expression for this matrix. We can write, if you do the partial derivative for f1 and f2 with respect to x1 and x2, we get the values for the matrix 0, 1, minus c by L cos x1 and 0. So you can easily find these terms from this f1, f2 function. Now we'll find the Jacobian matrix for the equilibrium point 0, 0. So let's find A, which is 0, 1 minus c by L cos x1, 0. At equilibrium point 0, 0, we are having 0, 1 cos for x1 equal to 0, cos x1 will be 1 minus c by L 0. So this is the matrix, Jacobian matrix for the equilibrium point 0, 0. Now, if you write in a state equation form, x dot, which is basically x1 dot, x2 dot, we can write 0, 1, z by L 0 into x1 and x2. Now, this is basically a linear time invariant system. Also, we can say linear system. And as you discussed earlier, that for LTI system, the equilibrium point is assumed to be 0. And if you consider this system here, this system, here also we can assume the equilibrium point 0, basically this system, equilibrium point also 0. So we can write, instead of this error form, this is basically error equation. This equation basically error equation. Instead of writing error equation in that variables, we can write also this expression also fine. It is basically that same expression you'll be having. So now from this the state equation we can obtain the state equation x1 dot equal to x2 and x2 dot equal to, we can write minus z upon L x1. So this is basically, I can say, linear system for the pendulum at equilibrium point 0, 0. Now we'll look the Jacobian matrix for the defined equilibrium point pi 0. So the Jacobian matrix at equilibrium point
Pi 0, we can write zero, 1, G by L cos x1, 0. At phi 0, we can write 0, 1. Cos pi actually minus 1, so minus minus plus G upon L and 0. And the corresponding state equation, equations for the pendulum system in linear regime, you can write x dot, which is x1 dot, x2 dot, or we can write 0, 1, G by L and 0 into x1, x2. And the corresponding state equations, if you separate the equations, x1 dot equal to x2 and x2 dot equal to C by L x1. So this is also linear system of the pendulum at equilibrium point pi 0. Let's stop it here in this lecture. In the next lecture, we'll be contouring how we can define the stability based on these obtained state equations, and also we'll connect the control part, how we can make the system controllable even the natural system is unstable. If you notice here, these systems, these equations, basically natural dynamics, which what we are getting from the original system. If you look the pendulum system, we have not assumed any perturbation or control in the system. So this is the original dynamics. Basically, this equation we obtained from the original dynamics. So this is, we can say, the natural linear system. So in the next lecture, we'll be talking how we can make the system stable using the control. Thank you very much. We'll continue from the next lecture.